Rotational dynamics. Here will be a tutorial on a couple of examples using what is essentially Newton's second law, but the angular version. Ask yourself what Newton's second law is. I've written it here. Maybe you have your own way of saying this, but this I would consider the linear version, the version that we're most familiar with. Try to figure out what it would say behind here for the analogy to that in the rotational sense. I like to write it, acceleration is the net force over the mass. Remember the word net. So pause the video, try to give the words in the equation behind this. So rotationally speaking, what we're saying is we've got angular acceleration. Ooh, here's a good one. It's caused by torque. And the moment of inertia is the quantity that resists acceleration. You might say a little more loosely, it's the quantity that resists motion in an angular sense or in a rotational sense. Now, these symbols, practice saying these out loud. Just, you know, nobody's listening to you. Just try, you know, this one right here. Just say these one by one. Pause the video. Angular acceleration, that's a Greek letter alpha. The sum of all torques, or the net torque, kind of think of it as the total torque, including clockwise, counterclockwise. Capital I, the moment of inertia. Try to think about what that is. Picture all those different distributions. It's the inertia of the rotating rigid body that resists that rotation because of not only its mass, but the way the mass is distributed. So here's an example. Write this down, pause it, and then listen to the explanation. First thing to notice is that I've got this basketball. If I'm exerting a force on it, on the edge, if I'm exerting the force on the edge, that means it's a tangential force, and that means it's the force, probably a frictional force, that was maximal in providing the acceleration. In other words, you're going to get the most torque out of it because it's totally perpendicular to the radius. Try drawing that out. I should have drawn that out, but I'm going to go quickly through this example. I'm going to calculate my moment of inertia for the basketball, and the moment of inertia of the basketball is here. And I use 2/3 mr squared because if you look it up, that is the expression for a thin spherical shell, not to be confused with a solid sphere. Seems pretty small, but then you consider we're talking about kilogram over a meter squared, so it's not very massive. I can figure out the rotational acceleration pretty easily in radians per second squared, given that it started from rest. And now I can plug into Newton's second law for rotation. Notice I put these two expressions equal to each other here. Makes sense. You can pause this at any time and think about it. And you end up solving here for the left side is a torque, but you solve for the force and you get 1.2 newtons. Noting that we're talking about we've converted the radius to into meters, not centimeters here. Now here we have an example that involves a common physics problem, classic situation. We'll call this the broccoli problem. Got this piece of broccoli that happens to be happens to be 1.2 kilograms, believe it or not. Yeah, I spent all that time looking at my own problem, trying to think about if that made sense. Yeah, I made a really massive piece of broccoli. We've got a pulley, but what's important here is if you think about this pulley is actually massive. We're not ignoring the mass anymore, so we have to think about the rotational inertia of the pulley and the rotational acceleration of the pulley and how that's going to resist. So write that problem down if you need to. First instinct, think about it. What are we going to do? We're going to draw forces and torques. Okay. Now the forces on the pulley is just the tension force. Think about what are the forces on the broccoli. There's tension and weight. Here's the part everybody gets confused about. This is the part you're going to want to listen to the explanation a few times or pause it or whatever. But the weight is greater than the tension. The weight here is greater than the tension. Think about why that would be. This thing is going to accelerate. The broccoli is accelerating downward. So this weight must be greater than this tension. However, given that the cord is considered massless, the tension that's on the pulley will be equal to the tension that's on the broccoli. Digest that, because look, this ain't true, meaning I've crossed out an equation. Tension is not equal to mg. That is the most common mistake. People look at this and they think that those are balanced forces, but what they're not accounting for is the simple fact that, hey, this thing is accelerating downward. We have an acceleration. So now I'm going to write down some equations and I'll explain each of these equations. I'm going to write down the fact that I've got Newton's second law rotationally and I've got Newton's second law linearly. So I have my linear and rotational versions of Newton's second law here and here. Linear, rotational. Linear, rotational. Where do they apply? Well, the rotational is applying to this thing. The linear is applying to the broccoli. So let's look at each of those. Okay, now this looks scary, don't freak out. But the sum of the torques is just R, the radius of the pulley, times the tension, and that equals 1/2 mr squared alpha. Why 1/2 mr squared? That's just my expression for the moment of inertia of a pulley, which is basically just a disk. And then the sum of the forces, if down is positive, you got mg minus ft equals ma. And here's my connection between the two. Now, this is really worth noting. Put a box around these, put a star. This is all the physics. This is all the physics. Everything else is going to be a bunch of algebra. You got to slow down, pause the video, understand my explanation for all of these things. Like, how did I know to do that? I knew to do that because I know I have rotational acceleration happening related to the causes of the acceleration, and I know I have linear acceleration happening related to the causes. And then there's the impeding factors, which are those inertia factors, namely the mass over here and the moment inertia over here. Here's my connection between the two. I know I have angular related to linear acceleration, and I'm going to plug in. Oh, look, one of the r's cancels. I've substituted here a over r. I'm starting to use a capital R because this is a general lowercase r. Plug it in over here, 1/2 ma, because look, I end up with this expression where tension is equal to 1/2 ma. Go over here, plug that in. Algebra. 4.8 meters per second squared is the angular acceleration. Now it's going to be easy to find the that's the linear acceleration. Now it's going to be easier to find the angular acceleration. 24 radians per second. How? Just plug into here. In other words, divide that 4.8 by the 0.2. Then the tension is easy to find. Because look, I have an expression right here where I know everything except the tension. Can plug back into that and you get 6 newtons. So to summarize, we just did some rotational dynamics, which really comes down to not conservation of energy, not conservation of momentum, but Newton's second law. We understand that we got to think about torque this time, moment of inertia this time. Here's a simple example. Here's a more complicated example that integrates both the linear and the rotational.